This video poster presents a book about Austral Asian tektites. It contains 42 chapters, as well as a dictionary and a reference list. After watching each video poster, you can download relevant chapters for detailed readings, using the link in the description below. The introduction chapter briefly gives an overview of the different forms that tektites have and also where they are found. Details are described in the following chapters. Many observations presented have not been described before, which may be due to the experience that, the eye sees all, but the mind shows us what we want to see.
The chemical composition of tektites in the Austral Asian strewn field is quite similar, for both splash form and muong-known tektites. But there are variations within each tektite, between specimens, and between sampling locations. Many analyses have been made, and give mostly similar results, both for major and trace elements with different explanations for the differences.
Splash-form tektites were created by an impact that formed a liquid from rocks. The development of the liquid followed many stages that can be illustrated by impact into water and by processes in water and vacs. The tektite strewn field in Southeast Asia covers about 10% of the Earth's surface, from southern Japan to north of Madagascar, and from southern China to Tasmania. It is butterfly-shaped, indicating that it was created by an oblique impact from north-northwest. Impact cratering have three stages. Stage 1 protrudes with high velocity in the impactor direction. Stage 2 excavates the crater by expelling material sidewards. In Stage 3 the crater collapses. In the first two stages, liquids form blankets with rounded edges, like in water. Blankets are stretched to the point where surface tension cannot hold the liquid together. The stretching is visible by stretched surface bubbles on some tektites, longitudinally and transversally. See the white and yellow arrows. Also the rounded edges are visible in cross sections. Vacs in lava lamps can illustrate the splitting of liquid spheres, forming two smaller spheres and a stick, a dumbbell, or a small sphere in between. Close-up images show such sticks and dumbbells in vacs, and frozen out in a tektite liquid. The videos show split in vacs, resulting in sticks, dumbbells, and small spheres in between. Flickering is from a 50 Hz light bulb, at 240 frames per second video recording. After some time the tektite liquid started to cool. Spheres cool from the outside by conduction and radiation from the top layer. When the outer layer, the shell, has solidified and compressed the still fluid nucleus, the shell cracks in 12 to 20 pieces upon impact, and the nucleus expands due to pressure release, and pops out. Apart from the tektites themselves, The material attached to their surfaces gives detailed information. Tektites from many areas in Southeast Asia are covered in quartz dust, comminuted quartz, often containing small mini-tektites, and pieces of carbonized wood. Splash form nucleus number 524 contained many mini-tektites, comminuted quartz, and carbonized wood, in the cavity, marked by the yellow arrow. It also contained a few larger quartz grains, zirconium grains, and tektite spalls. This is the total assembly from the cavity in tektite number 524. All white bars are 0.1 mm. A large assembly of comminuted quartz is attached to tektite number 388, also containing mini-tektites, and a larger quartz grain, with planar fractures. Two very rare micro-tektites were brushed of Muang Nong tektite number 1. Chapter 02 is about Philippine tektites. They look different than other tektites in Southeast Asia. Some spheres have wide grooves on their surfaces, with elevated areas in between. Some are named after their locations like Bicol, Anda, and Pangasinan. Blown by wind, above hurricane level, all the way to the Philippines, the outer layers cooled to a point where the shells and the nucleus could not separate upon landing. But the shell still cracked and the nucleus expanded due to pressure release, creating the grooves between. The volume of the grooves equals the volume expansion of the nucleus. Calculating this expansion for Bicol tektite number 206.1 gives a nucleus volume expansion of 97%. The size of the nucleus under shell pressure before cracking, and after pressure release, is illustrated by two white marbles. The bulk modulus at 10,000 Kelvin is calculated to 66 megapascal, which is around the tektite glass ultimate tensile strength of 60 to 100 megapascal, explaining why the shell cracks. Area measurement of the attached shells. The grooves themselves show three distinct features: bubble ridges, tunnel ridges, and Schlieren. Bubble ridges are sharp-edged and formed across the groove. Tunnel ridges formed along the grooves where the tunnel opened, between the shells. The tunnels combined mostly in three-way junctions. The base of the grooves can show Schlieren in random directions to the grooves, some overlaid by sharp-edged bubble ridges. At this junction, a three-way bubble ridge is seen, and two tunnel ridges are visible. See the yellow arrows. Anda tektites are specific as their grooves are divided into smaller grooves, all fanning out from the impact center. Right at the center, bubbles were pushed into the tektite nucleus, while small bubbles were ejected outwards in parallel, creating tunnels in the nucleus, before the shells popped off. This is a tiger claw, radiating from the percussion impact point. Close-up of Anda tektite number 236, showing the parallel grooves, yellow arrows, and bubble ridges, white arrows, radiating out from the impact point formed by 10 bubble cavities. Nucleus splash form tektite number 16, is from Da Lat in Vietnam, and shows many burst bubbles on the top and button surfaces. On the top surface a nice tiger claw radiates out from the percussion impact point. Three processes have been proposed for creation of bubbles: mechanical entrapment, physically dissolved gases, and by thermal volumetric changes, each resulting in slightly different bubble sizes versus rank. In splash-form tektites this leaves very few bubbles in the glass matrix but plenty of burst surface bubbles. This is illustrated by a polished splash form tektite without bubbles in the matrix, and the surfaces of tektite splash form nucleus number 539 and shell number 73, showing both the concave inside and convex outside. The outside contains many more burst bubbles than the inside. Some bubbles can coalesce, creating larger bubbles. Size ranking: the bubbles on the convex side of shell number 73 shows a steep gradient of small bubbles, and a very steep gradient for coalesced large bubbles. This could be creation type 1 from expelled mechanically entrapped gases. Size ranking: the bubbles on splash form nucleus number 16 show a less steep gradient for small bubbles, but the same steep gradient for coalesced bubbles as shell number 73. This could be creation type 2, from physically dissolved gases after pressure release. Large bubbles may not burst, but collapse instead, leaving a dome surrounded by a rim of stretched glass. Nucleation sites are impurities, like suspended particles or minute bubbles in a liquid, resulting in heterogeneous nucleation. In splash form tektites, many surface bubbles on shells contain partly melted quartz grains embedded in their inner surfaces. Such grains may have acted as nucleation sites, enabling the bubbles to grow large, quickly enough to ascend to the shell surface. Probably type 1 bubbles from mechanical entrapped gases. The sizes of the embedded grains are around 1/10 to 1/100th of a millimeter. Read more about splash form tektite bubble creation in Chapter 03, dependent on viscosity, temperature, and surface tension. Shells from splash form tektites are created when a tektite with low viscosity nucleus lands, and the solid shell breaks into pieces, being expelled, and the low viscosity nucleus pops out. Shells are distinctively different from spalls as they have flat edges. Spalls always have at least one sharp edge. An inner coating layer, between the solid shell and liquid nucleus, can sometimes be seen, probably remains of the softer nucleus. Shells have many forms, depending on the parent tektite, but normally they have 3 to 5 flat edges, mostly from pentagons, and are between a few millimeters to a centimeter in thickness. Often the convex sides of shells are filled with surface bubbles, while the concave inner sides are smooth, with only a few small bubbles. A hollow tektite would therefore have as many surface bubbles per square centimeter, on the concave inner, as on the convex outer side. As that is not the case, the parent tektite could not have been hollow. Instead, it contained the still low viscous nucleus. This image is from a book by French geologist Alfred Lacroix. Gas bubbles between the nucleus and the shell are compressed at the percussion point, to a degree where they are expelled, and create tunnels that radiate outwards on the surface of the nucleus below the shell, a tiger claw. Directly at the percussion point, gas is compressed inwards into the nucleus and creates deeper cavities. The landing site of the nucleus shows impact planes that have smoothed the surface. This is an illustration of phases in splash form tektites landing with a hard shell and a liquid nucleus, cracking and expelling shells, creating tunnels, a tiger claw, and impact planes on the nucleus. Close-up of a tunnel from splash form tektite number 16, showing its typical U-form with rounded ends after expansion. A composite image, showing a tiger claw radiating out, and cavities from inward compressed bubbles, at the percussion point. Part of a tiger claw, with one tunnel halfways extending into the nucleus, preserving. Spalls are flakes of material broken or knocked off a larger solid body. Spalls are often missing, while the footprint remains on the larger body. The footprint is evidenced by characteristic top lines between spalls, and as low collar edges on the larger body. The spall itself will always have at least one sharp edge, which makes it distinct from shells that have no sharp edges, all edges being flat. Flint tools showing characteristic top lines, marked with a T, between knocked off spalls, and a low collar, white arrow. Spalls can be knocked off both splash form shells and nuclei, leaving a low collar or top lines. A double top line on a splash form shell, similar to double top lines on flint. Thumbnail spalling after point impact, at white arrow, creating crescent-shaped spalls, still attached. Crescent-shaped thumbnail spalling, without spalls. Spalling on a Muongnong tektite, with chemical erosion, revealing detailed layering, surrounded by a small collar. Spall from a splash-form tektite, after point impact, showing the concentric lines from the shock wave. Spalling on Muongnong tektite with both main body and spall intact. Micrograph of spalling around a bubble in a splash-form tektite, showing schlieren. Cooling of splash-form tektites is a temperature and pressure-dependent process, from the moment of impact, where the temperature could be as high as 35,000 degrees Kelvin, and by cooling is an adiabatic and isentropic process of a supercritical silicate fluid, where liquid glass and glass vapor coexist. As the glass plume expanded and temperature and pressure dropped below the critical point, tektites and most microtektites were created on the liquid side of the phase diagram. Perhaps some microtektites were created on the vapor side. Pressure releases within few tenth of a second, the temperature could reach of 35,000 degrees Kelvin. Somewhere between 5,000 to 10,000 degrees Kelvin and 0.45 gigapascal, blue double arrow, the supercritical phase cools to the critical point, where liquid and vapor separates, and conductive cooling of the liquid tektites can start. This transition may take place in less than 0.25 seconds. Large impact crater temperature and pressure distribution. Splash-form tektites are created in the melt and vapor zones, above 60 gigapascal and from 1600 to 10,000 degrees Kelvin. Such temperatures and pressure are needed to create homogeneous glass. Such high temperatures and pressure can explain why splash-form tektites show convection schlieren, contain almost no inside bubbles, and very few volatile elements. They are very dry. This graph shows results from modeling the cooling of a splash-form sphere of radius 3.5 centimeters, assuming only the top layer cools by radiation, while inner layers cools by conduction. Read the chapter for detailed explanations. The cooling and cracking of shells during impact, and nuclei popping out, results in a variety of nuclei forms, dependent on viscosity. Low viscosity can result in flat nuclei, some rotated, and with a splash rim in the landing direction. Higher viscosity can result in disks and spheres. A crack is a line on the surface, along which it has split, without breaking all apart. On tektites, cracks can be found on splash-form shells and nuclei tektites. They can be distinguished from tunnels by their form. As seen from above, cracks are typically V-shaped, with a rather flat bed and steep banks, while tunnels have a constant width, a U-shaped bed, and the ends are rounded. Cracks may have stretched lines crossing the bed, that are different from bubble ridges. Cracks are created in glass with a surface solid enough to crack, forming the banks, and having a softer base that forms the bed and stretch lines. Comparing a V-shaped crack with a flat bed, to a U-shaped tunnel with rounded ends. 3 cracks on a splash-form nucleus, V-shaped, and with flat beds and stretch lines. Deformation of splash-form nuclei includes an endless variety of forms. Some patterns can be ascribed to viscosity and gravitational deformation. But also, the ejection path, rotation and downside heating of trapped air play a role. This is an illustration of nuclei forms, dependent on viscosity and gravity. High viscosity results in spheric nuclei, while lower viscosity results in flatter forms, some with a bottom cavity from trapped heated air, after landing. At even lower viscosity, The tektites may splash all out and show rotation. A disc-formed nucleus, where the downside is slightly concaved by heated air, probably when laying on the ground after popping out. A flattened nucleus splashed out after landing, with the downside taking form after the ground. Vague remnants after a tiger claw in the white square. The downside is compared to chocolate taking form after aluminum foil. Different nuclei forms showing both up and down sides. All low viscosity nuclei with splash rims, illustrated by a water balloon. Vague remnants after tiger claws in the white squares. Different nuclei forms, showing both up and down sides. Note the time series of onion-shaped nuclei to the right, from a large tail, to shrinking tails and an almost disappeared tail, sunk into the tektite, showing different viscosities. Muongnong, or layered tektites, are blocky layered pieces of black glass, found in a restricted area in Southeast Asia. They were named after the Muongnong village in Lao Pdr, where they were first described by Alfred Lacroix. They are part of the Southeast Asian tektite strewn field, but distinctively different from splash-form tektites. They have a bulky form, with a weight up to several kilograms, have distinct layering, and sometimes cracks on the surface, called bread crust, have degassing vents, and atmospheric gas composition in bubbles. They can show slope and flattening flow, and complex layering structures. The layers are often described as alternating light and dark layers. The difference is the contents of gas bubbles, that by reflection and refraction make the light layers look light, when, however, the glass itself has the same black color in both layer types. Alfred Lacroix described the Muongnong tektites as blocks, lay blocks, and described their discovery in large size. One measuring 0.3 by 0.2 meters, and at several kilograms, from south of Muongnong village in now Lao Pdr. Also, he mentions that he has seen considerable numbers of very small microscopic spherical gas bubbles, never large ones. This is a micrograph of new spallation of a light layer in Muongnong tektite number 1, with bubbles, and plenty of milky quartz grains, surrounded by white froth. The finer grain sizes that originally were in the sediments, from which the Muongnong tektites probably were created, can with some certainty be estimated from the layering, as no layer can be thinner than the particle size. This gives an idea of lower grain size in the silt class of 0.04 mm. An idea about the upper grain size class can be estimated from the largest remaining quartz grains in froth, around 1 to 2 mm. A pixel profile of tektite number 320 in the previous image shows 20 layers. The average layer thickness is 0.04 mm, giving a maximal grain size in the silt fraction. If the tektite flattened during melting, the grain size could be slightly larger. The polished and unpolished sides of Muongnong tektite number 461, showing light and dark layers, double-tipped bubbles, and froth. Sediment layers have different characteristics that evidence their creation. Apart from the layers themselves, sedimentary rocks can show cross-bedding, slope folds, differences in particle size, erosional truncation, graded bedding, and parting lineation. Slope folds are synsedimentary folds, created by slumping in the soft sediment. Cross-bedding requires a specific velocity of water flow, and graded bedding requires a change in velocity and grain size to separate grains, while parting lineation requires both specific grain sizes and specific current velocities. Rare cross-bedding can even be found in clay pools, formed at very low velocities or by stagnant water. Layers of different grain sizes in a muongnong tektite. Middle layers are fine-grained, silt or clay, and with very few bubbles. Layers above and below were coarser-grained. Yellow parts are laterite sediments residues, in vents and bubbles. Cross-bedding, erosional trincation, and graded bedding in a large muongnong tektite, visible after erosion. Micrograph, showing at least 2 cross-bedding layers in muongnong tektite number 546.1, sloping backwards, and with planar bedding erosional contact between. This indicates creation by water current, as wind cross-bedding typically slopes forwards. This thin section image shows one of the cross-beddings, from the previous image, in muongnong tektite number 546.1. Micrographs of layers in a spall from muongnong tektite number 592. From the spall side, left, and the surface side, right. The spall side also shows cracks radiating from top left. The layers on the surface side are made visible by chemical erosion, but are not visible on the spall side glass, other than as shadows from the surface side. Layer contours are made visible by chemical erosion, probably by difference in resistance to etching, not as difference in refractive indexes in the glass. Arrows point to same layers in the two images. A slope fold or convoluted laminae, in muongnong tektite. It can also be interpreted as a top-down view of bark-shaped migrating floccule ripple, with most of the top eroded away. Note the ridge in front of the eroded part marked with R. The most distinctive feature of muongnong tektites is probably the vents. Muongnong tektite number 606 shows parting lineation marked P, with vents aligned, and vent openings marked V, at both ends. Gases escaped between layers in same direction as parting lineation, creating vents towards least resistance, likely in a dry contemporary sediment. Parting lineation in sand is easily visible. Parting lineation also exists in finer grained sediments, but is not visible by the naked eye. Structures in muongnong tektites, and contemporary Korat Plateau sediments, are similar, and may evidence that they are related. The resemblance is especially high, when tektites are compared to silt and clay deposits in pools. Most sediments are created by surface runoff, during the wet season. The Mekong River tributaries are surrounded by laterite soils, providing most of the material. The river currents separate the sediments into different size and weight classes. The heaviest particles are transported as bedload, salting downstream, while finer particles are suspended, giving the Mekong River and tributary waters a brown or reddish color. Wind deposits sand grains in this clay and silt, and the sediment cracks resemble the bread crust of muongnong tektites. These images show the similarities between muongnong tektites and pool sediments. Layering, bread crust seen from the top, downsides, bread crust seen from the side, fault lines, and polygon shapes. Other morphological similarities between contemporary sediments and muongnong tektites include alternate layering and foldings. Specifically, the muongnong bread crust and polygon clay, seen from the side, has similar forms, like a crack with rounded bottoms from water flow. Some embedded in the tektite and sediment after being covered by new layers. Note the fault lines marked by the white arrow. During the dry season, large areas of the riverbed are exposed, and between large sand ripples and dunes, many small pools emerge. When repeatedly flooded by small water level fluctuations, very thin layers of suspended clay and silt settle in these pools, forming an expansive silt and clay sediment. It cracks upon drying, some with parting lineation and cross-bedding. The pool sediments show the same graded bedding as the layers in muongnong tektites. Some layers may be formed by wind, blowing in sand from the pool surroundings. In rare cases, even cross-bedding can be observed in clay pool blocks. Slope folds can be created in layered sediments by downslope flow or by overlaying pressure, resulting in S or Z-shaped folds. Folding flow can take place in the sediment or in the tektite glass. This video shows slope folding by overlaying pressure. Cross-bedding is rarely seen in Muongnong tektites and pool sediments. A three-layer cross-bedding sloping backwards, and with planar bedding erosional contact between. Flow direction from left to right. The backward sloping evidences flow by water as wind creates forward flow. The cross-bedding in thin sections is fainter, but still visible. Another example of cross-bedding in a Muongnong tektite. Like splash-form tektites, Muongnong tektites often have sediments attached to their surfaces, containing the same assembly. The assembly includes quartz grains, dark spheres with silt-sized quartz grains included, carbonized wood pieces, mini tektites and glass shards. Also, small pieces of pure sulfur are attached. Some of the larger quartz grains are battered into small pieces, that often split during polishing. A close-up of the black spheres, with silt-sized quartz grains included, probably in an iron and silica matrix. Larger battered quartz grains, probably from impact onto the Muongnong tektite, as earlier formation would have disintegrated them, before ending up in the tektite cavity. A thin section of a quartz grain, broken into small pieces, with crushed quartz powder between. A collage of mini tektites on a Muongnong tektite from Vientiane. The mini tektites are covered by quartz powder, comminuted quartz. The lower left image shows an exploded mini tektite after heating in a microwave oven, indicating that it contained gas or water bubbles that expanded. Battered quartz grains, under cross-polarized light, showing interference colors, evidencing that the individual grain pieces are now oriented at different crystal angles and thickness. These grains could not have been transported by water or wind, as they would have broken apart, but would rather have impacted the Muongnong tektite. Other Muongnong tektites, from Lao PDR, also contain comminuted quartz with carbonized wood and glass shards, in surface cavities. Like pool sediments, Muongnong tektites are only found in river valleys, often overlaid by other sediments. In some cases, the comminuted quartz grains found on both splash-form and Muongnong tektites covers a layer of Muongnong tektites. A watering hole, near the village of Muongnong, in Lao PDR, looks like kaolin, but is actually pure comminuted quartz, without iron oxide covering. These Muongnong tektites were found in a layer at the bottom of the watering hole, under the comminuted quartz. This Muongnong tektite, from Dalat in Vietnam, was cut to make a thin section, following the white line. The first image shows the top part and locations of impact quartz grains in microcraters, along the cutting line, marked A to E, and the location of an impact quartz grain in an uncut microcrater, is marked Q. The deformation of quartz crystals is dependent on pressure and temperature but also water contents, and their form of alpha quartz or beta quartz. An increase in water contents lowers the PT level, at which quartz crystals can deform, and changes the deformation type from mostly plastic to mostly brittle. Deformation can take place already at temperatures between 400 and 600 degrees Celsius. Probably through the quartz liquid transition interval, between Tg and Tm, quartz is more plastic at higher PT conditions, and more brittle at lower. This is the thin section, and the other side of the Muongnong tektite. During polishing, all the impact grains were polished off, leaving only the microcraters. Probable sediment cracks with rounded bases are marked with an S. Note, this side of the tektite has sediments attached. The sediments attached contain small quartz grains, comminuted quartz and mini tektites. This sediment was probably attached during the formation, as such an assembly would be unlikely to attach later. During an impact, with winds far above hurricane level, grains would be blown around in large quantities, some hitting and burying the tektite, still in the liquid transition interval. The grains themselves, probably also hot, flattened out during penetration, formed a microcrater, and left a partly cracked and crushed grain. This is the quartz grain remains in the microcrater location A, showing the flattened top surface, the cracks in the grain, and the crushed part below. A drawing to the right shows the details. This is the same grain in location A, seen from a 45-degree angle, from the top, and directly from the top. The top side is melted, perhaps from a following cover of hot comminuted quartz. This is also the impact grain in location A, in inverse colors, showing the impact direction, revealed by the minor impact bodies marked 1 and 2. Impact location B, shows a similar grain, with a flat top, a cracked grain, and quartz crushed at the bottom. To the left a smaller impact is visible. A drawing to the right shows the details. Also the top of these quartz grains are melted, both the large, and the small grain. The grain in location E has had a vertical impact, creating the crater, the cracked grain, and crushed quartz below. Some small engulfed grains remain, here green in the drawing. Also here there is a small impact to the left. The location E grain, in inverse colors, and the top side to the right. To the left is the crater from the thin section, where all the grain, and crushed quartz was polished away. Many Muongnong tektites contain such impact grains, visible in the surface, and revealed by a microcrater rim. Two more images, from another Muongnong tektite, with distinct impact crater rims, and impact grains preserved. Muongnong tektites were not the only rocks impacted by quartz grains in the Muongnong strewn field. This image is of a melted quartz stone, with an impact quartz grain, containing planar deformation features. Also the quartz stone was impacted by small iron spheres, marked I. Both have a small crater rim around, marked R. Read more about such rocks in later chapters. Parting lineation is a subtle sedimentary structure, in which grains are aligned in parallel lines or grooves, on the surface of a body of sand. Parting lineation is restricted to coarse silts as well as to fine and medium grain sands, with grain sizes of 0.016 to half a millimeter. They result from fairly high current velocities of 0.6 to 1.3 meters per second. The white line shows the parting lineation direction and parting lineation vents, penetrating out at the end of the tektite. The parting lineation is closely related to the vents in Muongnong tektites. Vents are created by degassing of the rock during heating. Vents are similar to vents in coke, after coal degassing. The vents follow the parting lineation where present, as gases penetrated through areas of least resistance. They are therefore visible at the ends of the tektites. This image shows 6 sides of a Muongnong tektite, with parting lineation in the yellow line directions, and vents penetrating out at the ends, marked C. This subtle sedimentary parting lineation structure may have played a central role in the formation of Muongnong tektites. In addition to the layering of the tektites, many Muongnong tektites show this lineation on the up and down sides. The image shows 6 sides of a Muongnong tektite, with parting lineation and vents penetrating out at the ends of the tektite. There is another type of vents in some Muongnong tektites, without parting lineation. Horizontal vents penetrated between layers, and is randomly oriented in the horizontal plane, resembling a web, formed between very fine-grained silt and clay layers. Bubbles are usually gases in a liquid. Because of the Marangoni effect, bubbles may remain intact if they ascend to the surface. In Muongnong tektites, the bubbles remained in the interior, as the viscosity was too high for the bubbles to ascend to the surface. A special kind of bubbles, here marked F, formed as a foam called froth, around a partly melted quartz grain, expanding and coalescing to form larger bubbles. Here compared to surface soap bubbles, and coalescing bubbles in a muongnong tektite. Despite high viscosity, some larger bubbles could slightly move, ending up as one-pointed bubbles with a flat head in the movement direction, here to the right. During cooling, most vents were closed inside the vent openings, but remained intact inside the tektites. They formed long, often two-pointed ends in the parting lineation direction. Image of typical froth, where milky quartz grains melted by conduction, and impurities in the grain expanded to create the froth around. If the whole grain melted, the bubbles could coalesce and the end stage be one large bubble. Bubbles in a muongnong tektite, after movement, leaving a string of very small bubbles behind, cut off from the main bubble. The allowed movement was about 1 mm, the length of the largest bubble. Remnants of a vent, marked V, and numerous bubbles in a light layer, probably mostly created from mechanically entrapped gases. The white spots are froth, elongated in the vent and parting lineation direction. Analysis of the gases in muongnong tektites agree with the atmospheric ratios. Assuming the bubbles created from mechanically entrapped and physically dissolved gases, during heating, remained at ambient atmospheric pressure, then cooling to 20 degrees Celsius, would leave a pressure between 0.1 and 0.3 atmospheres as measured in muongnong tektites. This would not be the case for gases in froth bubbles, expanding from impurities in milky quartz entrapped in higher viscosity tektite glass. Muongnong tektites show different kind of folding and deformation. Some folds may have been created while the sediment was still soft. Other folds were likely created by gravity at the peak of heating, when the glass mass flowed downslope, or by gravitational flattening of the whole tektite body, on a plane surface. This muongnong tektite has one fold. Seen from the side, a vent shows the parting lineation direction, always parallel to the layering. The top view shows the flow direction, marked by the white arrow, and two levees protruding from hitting obstructions, marked by white lines. This muongnong tektite shows SC folding, that has changed the layering and the direction of vents, marked by V, on the side view. From the top view, sticks show the rearrangement of vent outlets. Flattening flow is visible when a thin crust layer split into puzzle pieces, marked by an E, with stretched glass between. This was created by gravitational force or perhaps by weight of overlaying sediments. The yellow line shows the parting lineation direction. The presence of remnant magnetic inclination in tektite layers, of the paleomagnetic field of 28 degrees, 0.8 million years ago, at latitude 15 degrees north, with an average of 18 plus or minus 12 degree in muongnong tektites, indicates that the tektites were horizontal at the time of cooling below the Curie temperature of 585 degrees Celsius, as this inclination is only slightly lower than the average of the paleomagnetic field. Froth is a mass of bubbles in a liquid, like a foam. Froth of silica glass is plentiful in muongnong tektites. The froth was especially created when milky quartz grains melted, by heat conduction from the surrounding glass, often leaving remnants of the grain inside, surrounded by the silica glass froth. This image shows a muongnong tektite froth, surrounding a milky quartz remnant. And froth seen from the outside, where individual bubbles have partly collapsed during quenching. Most froth in muongnong tektites, with parting lineation, show flattening parallel to the lineation direction. Here images of froth surface, elongated froth, with no quartz grain remnant, and one slightly elongated froth with a quartz remnant. Some froth has coalesced to one bubble, here with small bubbles still attached to the surface. And a froth surface elongated parallel to the parting lineation direction. A collection of bubbles, from small and larger bubbles, almost all coalesced. Froth often contain remnants of the original milky quartz grain, from which the froth was created, when impurities expanded, during conductive heating from the surrounding tektite glass. Froth bubbles almost coalesced to one large bubble. The details in formation of froth from quartz can be explained from typical milky quartz grains in the Korat Plateau. The milky quartz, with impurities of gases of water and carbon dioxide etc., is surrounded by overgrowth quartz, without such impurities, but intermingled and overlaid by metal oxides, typically iron oxides. Heated by conduction from the surrounding glass, the grain starts to melt from outside. The bright halo between the froth and the tektite glass is the metal oxides, here silicium, titanium, aluminum, and iron, while the neoblast layer came from the quartz overgrowth. Detrital grain impurities then expand up to 10,000 times during heating, creating the froth, and exerting very high pressure inwards and outwards. For detailed explanations, read Chapter 18. This process can also explain the creation of coesite, a high-pressure polymorph of quartz. Here colored in orange. The image shows the quartz grain remnants, broken into puzzle pieces, transformed to coesite. Probably also the inside of the silica glass bubble cavities were transformed. Two processes described for the transformation of quartz to coesite can explain that. One process of direct subsolidus transformation from quartz, and another of subsolidus nucleation from highly densified diaplectic silica glass. The high pressure came from the expansion of impurities in the detrital quartz, creating the froth and transforming the puzzle quartz grains and part of the silica glass to coesite. The remaining and surrounding silica glass preserves the coesite, here gray, by acting as a pressure vessel, preventing the coesite to revert back to quartz during cooling. Two images showing the creation of froth from milky quartz grains in clay, used in a bronze kiln, now surrounded by melted glass and with milky quartz remnants inside, evidencing that this process can take place at temperatures below 2,200 degrees Celsius. There are two methods to distinguish between up and down sides of Muongnong tektites. The first method is the surface method. Looking at both sides, parallel to the layering, one will often look smooth, the downside, and the other looks cracked or with puzzle crust pieces, the upside. The other method is the slope method. It uses the precursor sediment rocks graded layering. Up and down sides can sometimes be found by looking at the slope of the layers. Larger grains, like quartz, settle first in sand and silt sediments, and smaller clay mineral grains settle last. This gives different slopes of sediment layers, visible when eroded by wind or by chemicals. More resistant parts, with quartz, erode more slowly than the clay minerals, leaving a steeper slope on the downside than the upside. For Muongnong tektites with flattening deformation, the puzzle crust pieces are on the top side. Like the bread crust example, the downside is smooth. Another Muongnong tektite, where the image with bread crust, to the left, likely is the upside, and the downside is shown on the right image. Measuring the pixel light intensity can show different slopes on the front and back sides of the graph tops. The black line is a 5 values moving average. Slopes calculated based on these pixel intensity values moving averages, the black line, show that the right side slope of 0.5972 is steeper than the left side slope of 0.4021, indicating up is on the left side. The white lines show slope equals 1. This is the same result as from the surface method. However, there are large variations, as R squared is low, so this method may not always be usable. Vents are tunnels, where gases escape the Muongnong tektites during heating. Horizontal vents were created if the precursor rock was very fine-grained, and had no parting lineation. Gases then escaped between layers, in a web-like structure of tunnels, ending at all the tektite sides. This is in stark contrast to parting lineation sediments, where degassing followed the lineation, and therefore exited only at the two ends of the tektite. Close-up images of web-formed vents, exiting between the fine-grained layers in the muong-nong tektite. Most vent openings are circular, while some have merged at the edge to become mouth-shaped. Many muong-nong tektites have not been cleaned by collectors, for very hard sediments. Sediments as hard as clay brick stones. Removing such sediments to reveal vent outlets underneath, some slightly oval-formed, probably from tektite flattening. The hot gases may have burned the clay, imparting the hardness and strength. This takes place around 1000 to 1200 degrees Celsius in clay. These close-up images show web-shaped vent tunnels. The base of the tunnels show crescent-shaped ridges from gas passage. The backside of the crescent ridges show the flow direction. This is a close-up of a collapsed vent exit, where the fine parallel layering converges to a point. The same collapsed vent opening as in the previous image, but here also seen from the top and in inverse colors. On many muong-nong tektites, vents are visible in the parting lineation direction. Some vents are exposed by erosion on the surface, and crescent-shaped ridges show the gas flow direction from the crescent backside, as well as the layering in the vents, marked A. After collapsing at the exit ends, vents can still be preserved inside the tektite as long bubbles. Vents were primarily created in the light layers, white arrows, that were coarser than the dark layers, yellow arrow, and therefore easier for gaseous elements to escape, following the parting lineation. Oval exit forms evidence tektite flattening. An internal 2 mm vent, white arrow, in the middle of a cut muong-nong tektite number 1 from Dalat. The vent is in the light layer, with lots of white froth. Inside this vent, are smaller uneroded vents with openings around 0.1 to 0.2 mm. An oval vent exit, with clay remnants, apparently heated to glass, forming a glass collar around the vent. Another vent exit, with clay remnants, forming a glass collar around the vent. Clay vents are vents, extending from tektite vents, into surrounding clay, probably laterite. The clay vents were created by heated gases, escaping the tektite during its creation. The inner side of the vent was melted. Further out the sediment was bloated, with smaller secondary vents. Further out again the sediment was heated but not bloated, and lastly surrounded by the parent sediment. Later iron and aluminum hydroxides were deposited, in agate-like layers, and diaspore, boehmite, and apatite crystals grew. The clay vent was covering a tektite vent, on muong-nong tektite 594, and became visible when the top was peeled off, leaving the tektite vent, marked B, next to a similar untouched clay vent, marked F. Close-up images of the peeled-off clay vent part, showing the melted inner rim, the bloated area next, followed by the unbloated aluminum and iron hydroxide layer, and last, the original sediment, with quartz grains, and a light matrix, unaffected by heat. A close-up image, showing these 5 areas. E, the vent, D, the partly melted inner rim, C, the bloated area, with many secondary smaller vents and crystal growth, B, the unbloated area with unmelted quartz grains, and an iron-aluminum matrix, and A, the original unaffected sediment, from which the vent was created. A drawing of the different layers of the clay vent. In Chapter 22, you can get a detailed description of the different parts of the clay vent. SEM, EDX image part of the inner side of the vent, showing partly melted quartz glass flow, and partly melted quartz grains, in the white iron oxide matrix. Point 19 is mostly a mix of iron and aluminum oxides, while point 20 is mostly iron oxide. A SEM, EDX image of a quartz grain in the bloated area, partly melted by conduction, leaving gaps to the surrounding iron-aluminum matrix. In the gaps, secondary crystal growth, containing aluminum, iron, and calcium, is not visible here, but can be seen in epifluorescence light images next. Epifluorescence light images, with enhanced colors of the previous grain, to the left, showing the small secondary multicolor crystal growths, probably diaspore and boehmite. Epifluorescence light image, of an attached particle in the vent tube, also with small secondary multicolor crystal growths, probably diaspore and boehmite. Erosion includes both mechanical abrasion and chemical weathering. Often mechanical and chemical erosion have worked on the same tektite. Chemical erosion is often visible in differences in glass surfaces. Uneroded surfaces are blank and shiny, and show no layering in Muongnong tektites, while chemically eroded glass is mate, and show irregular patterns, inclusive schlieren and layering, distinguishable from round or oval-shaped bubbles. Primarily, mechanical weathering is abrasion, and exfoliation like the Philippinites. Abrasion mainly attacks extruding areas, and can show thumbnail structures or spalling, while lower areas like bubble cavities can remain shining blank. Mechanical erosion can knock off spalls, leaving an impact point with concentric shockwaves around. The spall area can be shining blank compared to more eroded parts of the tektite. Spalling on a Muongnong tektite left a collar in the spalled area, marked with a C. It shows finer layering structures than the coarser outside area, showing that the outside area was chemically eroded for a longer time than the spalled area. A spalled area on a splash-form tektite, showing schlieren, after chemical erosion, and at the top right corner, part of the collar rim, at the white arrow. A Muongnong tektite seen from the side. The glass is made after chemical erosion, and at the center, many thumbnail spalls were knocked off. The layering was very fine, and only revealed where horizontal vents degassed. Another Muongnong tektite with spallation, leaving shining blank glass, in contrast to the remaining more mate, chemically eroded surface. Close-up images of an Onda tektite, showing thumbnail spalling on the top left and right images. The cavities are less eroded, and more blank, than the surroundings. The bubble cavities in the tunnel are also blank like the central bubbles. All cavities were protected by the higher elevated areas. A large splash-form tektite with a small, still blank, spall on the downside rim, marked by the yellow arrow. Similar small spalls on the top side, marked by white arrows, now almost eroded to the same level as the rest of the tektite surface. A heavily eroded splash-form tektite, seen from the top and button sides. The erosion may be regmaglip structures, from aerial ablation. On the top side a spall was knocked off, leaving a collar, and blank glass, with a quartz grain included, surrounded by a crater rim. The grain may have impacted when the tektite interior was still elastic. Australites, or Australian tektites, are regarded as being part of the Austral Asian strewn field. They have similar chemical composition and age as tektites from Southeast Asia, but are very small. They have been divided into 9 different groups according to their form: buttons, lenses, round cores, ovals, oval cores, boats, canoes, dumbbells, and teardrops. On average, the Australites have rest masses around 1 to 2 grams, and they are ablated by atmospheric re-entry, and show schlieren, like splash-form tektites. Being that small, The parent tektites must also have been quite small. Both small and larger tektites could survive the atmospheric re-entry, but larger australites are not found, except for a few in a part of Western Australia. The modeled trajectory of tektite atmospheric re-entry, by weight and re-entry angle, over Australia, assuming dense atmosphere starts at 80,000 meters altitude. Steep entry angles decelerates in a straight line, before falling vertically to the ground, while oblique angles decelerates at higher altitudes, before falling vertically. Heavier tektites with higher momentum takes longer to decelerate. Modeling the rest mass of Australian tektites, compared to 6,552 Australian tektites, fits well, assuming the start masses were between 5 and 10 grams, and re-entry angles between 3, 5, and 7 degrees. Modeling a 1 kg tektite trajectory, based on start velocity and ejected start angle, shows the rest masses after atmospheric re-entry, and shows which tektites would undershoot or overshoot Australia or exit to space. Some would disintegrate if atmospheric pressure exceeded the tektite's tensile strength, others would fully evaporate. Modeled ablation percent, depending on re-entry angle, for 1 kg, 0.01 kg and 0.005 kg tektites. Low angles provide most ablation, and the higher mass of the tektite, the more is relatively ablated. See blue versus green bars. Larger tektites have higher momentum, and decelerates more slowly than small tektites, and thereby ablate relatively more at same re-entry angle, however still retain larger rest masses, because of higher start masses. Example of a 76 gram tektite, re-entering the atmosphere, dependent on re-entry angle and velocity. Between the blue and yellow lines, the tektite would disintegrate as the atmospheric pressure exceeds the tektite tensile strength. Below the blue line, ablation takes place, and above the yellow line, the tektite escapes to space.
Impact on Earth by a celestial body, a meteor, or a comet, is the likely event that created the Austral Asian tektite strewn field. The size of the strewn field, from southern China to Tasmania, and from south of Japan to Madagascar, suggests that a large 32 to 114 kilometers in diameter, and more than 3 kilometers deep crater should have formed, somewhere in Southeast Asia. Such a crater has never been found, despite intensive geological mapping and oil explorations. A comet impact would create a fireball and irradiate an area from the center to the horizon, except where radiation would be blocked by mountains. The image shows a viewshed from 60 kilometers altitude, with center at the Yellow Star, in Southeast Asia. Oblique impacts can create elliptical craters, if the impact angle is below 12 degrees. The impact can be divided into 3 stages, each having characteristic vertical ejecta patterns: 1, an impact stage, 2, an excavation stage, and 3, a later stage. The impact stage creates a crater, a fireball radiating to the view-shed horizon, and earthquakes moving outwards at 5 kilometers per second. In stage 2, the excavation takes place, and material at the front end is expelled forwards at almost the same speed as the impactor. This would have created the Australian tektites, expelled above the atmosphere, and re-entering over Australia and Tasmania. The temperature can here be very high, above 10,000 degrees Celsius. In stage 3, a large ejecta curtain is ploughed out sidewards at a lower speed, creating a transient crater. This stage may take place within few minutes after stage 1, and create the other larger splash-form tektites, some carried all the way to the Philippines, by above hurricane winds. Finally, this transient crater collapses into the final crater. The result was a butterfly-formed ejecta, covering more than 10% of the Earth's surface, and probably somehow send microtektites all the way to Antarctica. Using Earth Impact Effects program to model an oblique 5 degrees impact, by a 4-kilometer diameter comet, into sedimentary rocks, gives a final crater diameter of 20.3 kilometers, and an irradiation radius of 814 kilometers. The size and composition of the impactor is unknown and the results therefore only indicative. Such an impact would create high-pressure polymorphs of different minerals, especially quartz. These polymorphs can survive in stability zones around the crater. The brown line shows the stability zone for rhyodite, and the blue line the stability zone for coesite. The above hurricane winds would pick up such grains and bombard everything in the vicinity. This graph shows the difference between a ballistic ejecta model and an atmosphere interaction model. In the atmosphere interaction model, the hot atmosphere carries ejecta far away and for a long time suspends smaller fragments, smaller size frequency distribution. Even small fragment could reach the Philippines. The impact created 2 distinct tektites, splash-form and muong-nong tektites. Apart from their ages, they differ in more than 20 parameters. This indicates that their creation was very different. The splash forms were probably created by a fluid ejecta in the excavation stages, while the muong-nong tektites were heated on the ground by hot ejecta. This is supported by the chemical composition of muong-nong tektites, similar to the clay pool sediments, and their similar morphology. This can also explain how their layering was preserved, how vents were created and why downhill flow and flattening flow was always parallel to the layering. It also explains that comminuted quartz is attached to tektites all over Southeast Asia. The chemical composition of tektites in the Austral Asian strewn field is quite similar, for both splash form and muong-known tektites. But there are variations within each tektite, between specimens, and between sampling locations. Many analyses have been made, and give mostly similar results, both for major and trace elements with different explanations for the differences. Read about the beryllium and iridium contents, and the contents of high-pressure polymorphs like cosite, stishovite and rhyodite. Read about the differences between splash form, muong-known, and microtektites, in chemical composition, locations, color and probable creations. The muong-known tektites are compared to Mekong River bank sediments, that have a composition almost equal to the tektites, and fits within other attempts to predict a precursor's chemical composition. The major oxide elements fit at an R² of 0.9991. Comparing the Mekong River bank sediments to available muong-known trace elements gives an R² value of 0.9449. Almost as high a value as for major elements, indicating that bank sediments could be the precursors to muong-known tektites. Mekong River bank sediments are also found in clay pools, deposited between sand bottom ripples, during the dry season. They show alternating layering from subsequent inflow of suspended sediments, and mixing with aeolian contribution of quartz grains. During drying they crack, leaving forms and morphology similar to muong-known tektites. It has been proposed that Southeast Asian tektites were created by post-Archean sediments, indicative of Jurassic sedimentary rocks, aged around 167 million years old. Four different mixing were proposed, all of which correlate at very high values to mainstream bank sediments. Some of the trace elements in Southeast Asian tektites act as fluxes and superfluxes, that lowers the melting temperature. And colorant trace elements can change the tektite's apparent color. This can explain the variation in colors between splash form, muong-known, and microtektites, in combination with dissociation-dependent temperatures. The similarities in chemical composition between Mekong River bank sediments and muong-known tektites, together with the similarities in morphology, indicates that exposed Mekong River bank sediments were precursors of muong-known tektites, and that heating took place on the ground, under a thick layer of comminuted quartz ejecta, from the impact. The Korat Plateau is a plateau in the northeastern region of Thailand. The average elevation is 200 meters and it covers an area of about 155,000 square kilometers. The mountains in the west are up to 1,200 meters above sea level, and the lowest point is 110 meters, at the rivers T and Mun confluence of the Mekong. The plateau is divided by the Phu Phan Mountains into two basins, the northern Sakon Nakhon Basin, and the southern Korat Basin. The red areas are high terraces. If a celestial impact took place here, evidence, other than a crater should exist. The plateau is tilted towards the southeast, and drained by the Chi and Mun rivers, tributaries to the Mekong. The Korat Basin is enclosed by the Phu Phan Range to the northeast, the Phetchabun Mountains and the Dong Phaya Yen Mountains in the west, the Sankambang Range in the southwest, and the Phnom Dangrek Range in the south. The image shows the setting of the Korat Plateau geology. The basic sandstone formations are deposited like a stack of plates with ages from Jurassic to Tertiary. The high terraces have been described in different ways, as relict river terraces and as relicts from major flooding. The high terraces are 40 to 60 meters deep and consist of pebbles, gravels of quartz, chert, andesite, sandstone, sand, etc. On top is deposited a loess-like sediment of clays to fine sands with reddish color. This sediment is also known as Yasathan soil. This morphology is not in line with river terraces. Also, they are only on one side of the Mun and Chi rivers with no elevation on their hind side. Also, the Yasathan soil shows no fluvial structures, but a homogeneous layer of sediments with gravel and splash-formed tektites at the bottom. Probably commenced by sedimentation in a vertical direction, indicated by broken grains and the lack of fluvial structures. The Yasathan soil contains glass shards, mini tektites and carbonized wood pieces, and specifically quartz grains in fine to very fine silt sizes, a sediment not found elsewhere in the Mekong River. The lower terraces, between the high terraces and the tributary rivers Mun and Chi, are exposed in numerous gravel pits. Above bedrock, the cross-sections are dominated by gravel and sand with chaotically occurrences of carbonized tree trunks, pure sulfur deposits and fine, to very fine silt quartz grains in clumps. Also splash-formed tektites are found. Low terrace gravel pit with carbonized wood, pure sulfur, iron concretions, chert, and comminuted gray, fine to very fine silt quartz grains in clumps. The high and low terraces creation, on the Korat Plateau, has been ascribed to different processes. The high terraces as river terraces deposited by a large river and probably later elevated to their present level. The low terraces as fluvial deposits formed by the Chi and Mun rivers, and the Yasathan soil as aeolian, loess-like, in origin, or even created by termite bioturbation. None of these theories, for the formation of the quaternary sediments, are likely. The high terraces are only on the left side of the Chi River and only on the right side of the Mun River, on their mountain sides. The actual height of the high terraces would require a really large river to form, and no large river bed is reported from these areas. An alternative catastrophic creation cycle is proposed here, based on the terrace compositions and geomorphological structures in the area, illustrated by profiles, 3D elevation models, and animations. River beds are short, and cross-sections of the river valleys very wide, with headwaters on small plateaus. The river beds and banks are U-shaped, in a complex combined pattern. These valleys are similar to chaotic labyrinth channels known as the channeled scablands in the USA. Based on the chaotic sediment layers in the high and low terraces, and the inclusion of tektites and very fine quartz grains, in the 0.02 to 0.002 mm sediment grain size, it is suggested that these structures, U-shaped valleys, high terraces and the chaotic unit A of the lower terraces, were created by a celestial impact. This caused major landslides, with following gravel and debris flow, driven by the excessive downpour, and later provided a constant supply of ejecta grains, Yasathan soil, including fine-grained quartz, settling vertically down through the water. The end result was tremendous turbulent flash flows, with a front lobe of mixed debris creating the low terraces, followed by a mud flow containing even large boulders, fanning out and creating the high terraces. Possibly the impact created a phreatic volcanic eruption, and a 0.92 million years old flood basalt was formed. The impact site may be beneath these basalt areas. This can also explain why wide valleys start up to 70 meters high in the air, as landslides remove material behind and then flush to create the terraces. Cross-sections of flash flow valleys. Dark lines show present river valleys. Light blue lines show potential flash flow levels 10 to 60 meters high, enough to cover the outer edges of flow basalt by sand and gravel. Locations of sand and gravel quarries, high above present river valleys, on top of the basalt, indicate the basalt flow took place before the flash flows. The brown layer shows the top of the basalts. The end result was the creation of low and high terraces, by flash flooding, partly covering the flow basalt and creating new ways for the tributaries to the Mun and Chi rivers. The hilly landscape behind was depleted in sediments, leaving sharp peaks and large flash flood reservoirs, today used as irrigation reservoirs. Effects on Earth by impact of a celestial body can be devastating. The body that created the Austral Asian tektites must have released enormous amounts of energy to create the world's largest strewn field. Apart from craters, historical impacts have shown evidence of other effects. On small scale, the Tunguska meteor fall in 1908, and the more recent Chelyabinsk meteor, evidence the potential effects. For the Austral Asian impact, the tektites and microtektites are the main indicators. The Tunguska event showed startling evidence of the impact, by flattening a large area of forest, leaving tree trunks pointing away from the hypocenter, broken, uprooted, irradiated and incinerated on one side, and stripped of branches. Surviving trees still evidence the impact by burned wood inside trunks in direction of the hypocenter. Carbonized wood is well known from volcanic eruptions. Creating carbonized wood and Muongnong tektites covered on the ground by 2000 degrees Celsius hot ejecta by conduction, is calculated for a hypothetical Muongnong tektite precursor of clay, measuring 10 by 5 by 3 centimeters, heated on 5 sides, and a tree trunk 10 meters long, measuring 30 by 30 centimeters, and heated on 5 sides. It would take about 10 hours to heat the trunk to 400 degrees Celsius, while the tektite precursor would heat to 2000 degrees Celsius in just 7 minutes. Carbonization of wood and melting of silt/clay stones is also simulated using microwaves. Microwaves penetrate the whole item, and can therefore provide similar results as longer time conduction, creating carbonized wood and Muongnong tektites. The simulation shows the creation of carbonized wood after 10 minutes, and start of clay melting into glass, with vents, after 12 minutes, at around 700 degrees Celsius. Carbonization of wood is different from forest fire charcoal. Forest fires burn from the bark on the outside, typically leaving part of the trunk and root inside, unburned. Often larger branches are also preserved. A 7 meters long carbonized tree trunk from Ban the Chong gravel pit. Uprooted with the top broken off, one side incinerated, with no branches, and fully carbonized. Smaller pieces of carbonized wood, incinerated on one side, still with bark on the other side, covered with incrustations of pyrite in silica. Large clumps of pure sulfur on a rock, and as pyrite incrustations, on the bark side of a carbonized piece of wood. Micrographs showing incrustations of silica and pyrite on the bark side, and tracheate vents, after degassing, showing the wood was non-homogenized, which would have left only tracheate cell walls. In the Ban Ta Chong gravel pit, many different rock types are found. Light brown and dark brown chert, pure sulfur, iron concretions, comminuted quartz accretions, basalt, quartz grains with planar fractures and planar deformation features, ballan quartz, carbonized wood, zircon grains, gravel, and animal and plant fossils. Each rock type is described in the following chapters. Light and dark brown chert in the pit turn out to be melted or partly melted sandstone, evidenced by layering and crystal remains in their matrix. They have also been bombarded, like muong-nong tektites, leaving craters on the surface and aggregates of quartz and iron spheres, included in their matrix. During heating and melting, new minerals like barite formed, by rhomboid growth, and iron spheres and small quartz grains bombarded the rock. Iron spheres as small as 0.05 mm have low enough viscosity to splash out on the surface. And aggregate clumps of quartz grains and iron spheres could make small impact craters on the surface, with pronounced rims. Bizarre situations were preserved. Here a quartz grain glued to two walls by tiny iron spheres. A dark brown chert, showing layering on the side view to the right, and embedded quartz grains on the bottom side, with some grains still attached, and some leaving their imprint marks. This surface of a light brown chert shows small iron spheres after impact, surrounded by shock waves and covered by a thin layer of quartz glass. Seen from the side, the thin layer of glass covers a deeper layer, with many red iron spheres, and a yet deeper layer, where barite crystals formed, and where very small zircon grains survived the heating. Cross-sections of a light brown chert shows the impact of a quartz aggregate, from the direction of the white arrow, partly melted in different stages. Very small quartz grains, with planar deformation features, impacted the still low viscosity rock, embedding itself in the surface, and probably a bit of its own surface was melted, revealing the planar deformation features. Dark brown chert, showing impact craters with converging lines. Small craters overlap the larger crater rim. The impactor, here removed, was aggregates of quartz grains and iron spheres. A quartz impact grain, all engulfed under the chert surface, partly melted at the bottom, leaving large concentric shock waves in the chert matrix. The matrix also contains red iron spheres. The so-called chert is not chert, but metamorphed quartz stones, that could be called quartz tektites. In the Ban Ta Chong gravel pit, there are large lumps of pure sulfur on the surface. Even embedded in the comminuted quartz accretions, sulfur is found, and in the large lumps, mixed with quartz and carbonized wood pieces. Iron accretions are also plenty, with a very mixed composition, consisting of a fine-grained matrix of comminuted quartz, iron and manganese, mixed with larger quartz grains and carbonized wood. Larger iron drops show two distinct impact features. One shows Newman lamellae at the bottom and rosettes on the top. Another show donut shape on the top, after oscillation. Both iron drops probably impacted the iron accretion in a viscous stage, enabling these structures to evolve. A micrograph of a larger quartz grain, surrounded by comminuted quartz. Spectrum of a piece of iron accretion, revealing the fine-grained matrix composition of silica, manganese and iron. A piece of carbonized wood to the right. The Khorat Plateau sandstones contain manganese and iron, often as ferrocrete and manganocrete, providing the parent material to form the iron accretions, mixed with comminuted quartz and carbonized wood. Another iron accretion shows similar interior, but with larger quartz grains attached to the surface, by bombardment or by landing pickup. Larger assemblies of comminuted quartz, with carbonized wood pieces, in the interior. Micrographs of a piece of carbonized wood, and the fine-grained matrix with larger quartz grains. The temperature at which the accretions were created could be as low as 1,300 degrees Celsius. However, the presence of oxides, instead of pure metals, may have required somewhat higher temperatures. The ash found in the Ban the Chong pit is mixed with clay and gravel, but still also remain in unmixed lumps, with a distinct gray color, separating it from the brown reddish color of the remaining sediments. Some of it formed accretions, similar to accretionary lapilli, here with two layers, an inner nucleus and an outer shell. On the outside larger quartz grains with special features were attached. Apart from comminuted quartz grains in the very fine silt to clay fraction, the ash also contains minitektites. Most quartz grains are without metal oxide coating, giving the sediment the gray color. The ash also contains small balls of iron, with very small quartz grains included, sulfur and tiny pieces of carbonized wood. A number of minitektites were found. They are not spalls as they have no sharp edges. Gypsum in the accretion, formed after evaporation of water. The formation of the accretion may have been similar to accretionary lapilli from volcanoes, where water and here dissolved gypsum provided the binding. Glass shards were also found. They have slight greenish coloring and could be from tektites. The fine-grained comminuted quartz is also present in the Yasothon soil, but not in Mekong River sediments. This fine-grained comminuted quartz can be used as a tracer in the Khorat Plateau, as it is attached to the surfaces of tektites from Ban the Chong, Dalat, Kon Tum, Muong Nong, Vientiane and is found in Yasothon soils as well as iron concretions. The larger quartz grains attached to the outside of the accretion show distinct features from bombardment, like shock waves and impact grain remnants. And from quencing, forming palisade quartz, around impact grains, and matrix cracking. Quartz sand grains from the Ban the Chong gravel pit show shock metamorphic features like fractures and planar fractures, that develop at lowest impact pressures. Also plastic deformation and ballen quartz are found. Both are temperature and pressure dependent. Ballen quartz requires a solid-to-solid transition from alpha quartz to diaplectic quartz glass, forming the ballen structure, and then a back transformation to alpha cristabolite or alpha quartz. Many quartz grains are broken, but still preserved in one grain, with larger pieces surrounded by pulverized quartz. These grains could not sustain fluvial transport without breaking apart. Some grains show planar fractures or possibly planar deformation features with decorations. An enigmatic rock is also found in the Ban Cha Chong gravel pit. At first glance it looks like a claystone, but has properties linking it to volcanism and conglomerates. The sticks show directions of degassing vents. Some of these claystones contain lenticular pieces of chert in their matrix, and are glued to iron concretions, containing different sizes of quartz grains. The interior shows signs of partly melting, by vents and flow structures. And the chert lenses show melt intrusion from the matrix. Here modeled in 3D using SketchUp, showing layers converging to a point upon collapse. Some of the claystones show vents on all sides, indicating that there was no preferred layering structure guiding the escape of gases. Chemically, the matrix consists of large plagioclase crystals with quartz, cristobalite and lecitolyrite, here shown in cross-polar light to the left. Enlarged images of plagioclase crystals in reflected light and cross-polar light. Top right, a cristobalite grain from obsidian. This chemical composition indicate a volcanic origin. Cross-polar light on top and reflected light at the bottom, showing cristobalite grains cracking, probably during quenching and shrinking 3 to 4% reverting from beta cristobalite to alpha cristobalite. The chemical composition indicate a volcanic origin, while the inclusion of chert lenses, vent opening and their collapse, attachment of iron concretions point to exposure to the impact event. An enigmatic rock. Khorat basalt eruptions. The basalt eruptions are part of a larger Cenozoic intraplate volcanism, less than 16 million years old, around the South China Sea, from the Hainan mantle plume. Khorat Plateau basalt is the youngest in the Cenozoic basalt. It is located in a line east to west, south of, and parallel to the Mun River. The westerly parts are the youngest, 0.92 plus minus 0.3 million years, and the easterly parts 3.28 plus minus 0.48 million years. The youngest basalt uncertainty of plus minus 0.3 million years spans the tektite creation impact time, around 0.789 million years ago. Late Cenozoic volcanic rocks are mainly distributed within the red circle, dashed line, and include the Lijiao Peninsula, Hainan Island, Pearl River Mouth Basin, Bibu Gulf, Indochina Block and the Khorat Plateau. Sketch map of Thailand and surrounding regions showing the late Cenozoic volcanic centers with ages, principal Cenozoic faults and Paleotethous sutures, national boundaries and sampling locations. Detailed geological map of the Nakhon Ratchasima basalt. The basalt age is 0.92 plus minus 0.3 million years. The cross-section D is displayed below. Dark blue lines are 200-meter contours, the yellow lines are 250-meter contours and the light blue lines are 300-meter contours. Short dotted lines show fault lines. Note the division between the large flow basalt and a smaller area separated by the KPP, Hufan sandstone. The creation is suggested to be a two-step event, triggered by a celestial body impact, that created the Austral Asian tektites. First stage was a phreatic eruption, mostly of gases, triggered by the sudden pressure release in the Hainan mantle plume, when the transient crater was excavated down to 5 kilometers depth. This would mostly release sulfur, carbon oxide and other volatiles, as the quartz sandstones were already comminuted and expelled by a hydrothermal groundwater explosion from the impact. The second stage was a basalt flow, filling the final crater with different layers of basalt. Later a torrential flash flooding took place, creating the present landscape and covering the edges of the basalt up to 60 meters elevation with gravel, creating the sharp basalt edges, by erosion. Basalts in the Nakhon-Ratchasima province are classified as subalkali basalts and in some sources as tracheobasalt, and contain phenocrysts, mostly of olivine, clinopyroxene, plagioclase and magnetite. Alteration products are normally ittingsite. The Ban the Chong gravel quarry contains small basalt rock fragments. They have a fine-grained dark, almost black matrix, with some special surface structures. This image shows a cavity surrounded by a rim, and filled with partly melted material, probably clay and 2 melted quartz plumes, small quartz grains and spherical iron drops. The spherical iron drops are similar to drops found on chert and muong nong tektites. Other small basalt rocks from the Ban the Chong gravel pit show a matrix with plagioclase crystals, melted material and conchoidal fractured olivine crystals. Some olivine apparently transformed partly to ittingsite. In the vesicles, some minerals have melted, covering the inside by layers of melted olivine and plagioclase and other dark minerals. These morphological features are like the features in basalt from the Sila Chokchai basalt, found 100 km south of Nakhon-Ratchasima. The Sila Chokchai quarry contains different layers of volcanic origin. The basalt plume itself is very flat, indicating a high viscosity eruption, where basalt flowed out in different directions, from several veins. The basalts are subalkali basalt, classified by some as trachybasalt. Basalt from Sila Chokchai quarry, Nakhon-Ratchasima, Thailand, contains mainly plagioclase. And a darker basalt with many plagioclase-covered vesicles with melted drops of plagioclase and olivine on the inside. Another type has few vesicles, but many large ittingsite and olivine phenocrysts in the dark matrix. Micrographs of basalt rocks showing hornblende or clinopyroxene, with reaction rims, melted plagioclase, orthoclase and olivine with conchoidal fractures. Vesicles with melted plagioclase walls, surrounded by a plagioclase and clinopyroxene phenocrysts rich matrix, with magnetite. On the inside surface of the vesicles, numerous melted olivine and smaller plagioclase spheres, evidencing gas hot enough to melt such olivine and plagioclase. Basalt from Sila Chokchai basalt quarry, Nakhon-Ratchasima, Thailand. A layer of almost pure plagioclase. Some changed plagioclase crystals show discontinued zoning, evidencing their magma chamber origin, and sudden pressure release, probably from a mush of almost pure plagioclase. The Nakhon-Ratchasima basalt with elevation contours and fault lines. The yellow fault lines are radially pointing towards the basalt eruption centers and crossing the black 250 meters contour line. This line delineates the flat basalt and the steeper slopes from the surrounding areas. The slope profile shows the steep slope at the 250 meters contour line, perhaps created by flash flow erosion. The basalt plateaus show at least 10 different eruption centers, numbered 1 to 10. The same basalt area, but overlaid by gravity anomaly data as the first vertical derivative of the isostatic residual. The gravity data shows 7 blue areas with low gravity, and a central red, higher gravity area, under the basalt, which extends north and west. Dotted ellipse shows a potential oblique impact crater, around 20 kilometers in diameter. The same gravity anomaly data as the first vertical derivative of the isostatic residual. This gravity anomaly has the same structure as a proposed impact crater, near Bow City, Alberta, Canada, showed in a similar isopack map. Similarities between Yasothon soil, Ban the Chang gravel, comminuted gray quartz and the Sila basalt quarry rocks, point to a possible relation between the Southeast Asian impact and volcanic eruption of flood basalt in the southern part of Nakhon Ratchasima province in Thailand. Ballan quartz, grain with plastic deformation, planar deformation features, a crushed grain with quartz powder between larger pieces, and a grain with planar fractures, from Ban the Chang gravel pit. The Yasothon soil from the Korat Plateau, which is not a soil, but a sediment, contains comminuted quartz of 0.02 to 0.002 mm. It contains glass shards, mini tektites and tektite spalls, carbonized wood and iron spheres, with silt-size quartz grains included. Muong Nong tektite from Vientiane, Lao People's Democratic Republic was covered in silt-size quartz grains, that also contained glass shards, mini tektites, carbonized wood, and an iron sphere with silt-size quartz grains. A comminuted quartz accretion from Ban the Chang. It contains glass shards, mini tektites, carbonized wood and iron spheres with silt-size quartz grains. An iron accretion from Ban the Chang, with comminuted quartz grains, and iron spheres with silt-size quartz grains included. Similar silt-size quartz grains covering Muong Nong tektite from Vientiane. The map shows location where comminuted quartz was found covering splash form and Muong Nong tektites. A splash form tektite from Dalat, the surface covered by comminuted quartz, here brushed off, containing mini tektite in carbonized wood. Compared to comminuted quartz from Muong Nong village irrigation pond in Lao People's Democratic Republic. A splash form tektite from Con Tum, Vietnam, with comminuted quartz grains, mini tektites, glass shards and carbonized wood. Ban the Chang chert, showing melted quartz grain embedded in the surface of the quartz matrix. It is 0.1 mm, has a wagely developed impact rim and contains planar deformation features. Iron drop with impact rims and two splashed iron spheres with silt-size quartz grains embedded. Quartz grains embedded into bottom side of melted quartz rock. Ban the Chang non-homogenized carbonized wood. Carbonized trunks with one side incinerated, bark on the other. Gray silt quartz grains clumps, brown gravel and sulfur. Octahedral magnetite crystals and impact craters in Braun chert, including impactor grains, dotted with iron spheres. Coesite, colored orange, in core remain and inside froth bubbles, created by high bubble pressure. Froth from outside with partly collapsed bubbles. Milky quartz inside froth and froth without central grain remains. Quartz grain with impact locations, view after cutting. Impactor grain, flattened at the top and crushed at the bottom. A smaller melted crater-like grain to the left, with apparent melt below. Drawing and top view of the flattened impactor grain. Thin section of first image, shows that impactor grains are polished away. Carbonized tree trunks in the Ban the Chang gravel pit. Incinerated on one side and with bark on the opposite side and the top broken off. Different from wood fire, right image, that burns from the outside, leaving wood in the interior. Middle Pleistocene supereruption of Toba, at 788 ± 2.2 thousand years. This time interval overlaps the tektite ages of 789,000 years. There may be a connection between the Southeast Asian impact and the Toba eruption, as volcanic glass is found in sediments with microtektites, far to the east of the volcano. Battered grains, south of Nakhon Ratchasima, in Thailand, the impact shock wave battered the sandstone grains, and upon pressure relaxation created a hydrothermal explosion, from evaporated groundwater, expelling the comminuted silt quartz grains into a dust plume, and excavating a transient crater to a depth of 5 kilometers, 20 to 30 kilometers wide, where the Hainan magma plume became exposed, resulting in a phreatic eruption, momentarily releasing the gas pressure from further down. Like chert rocks, Muongnong tektites were also bombarded, leaving impactor grains in their craters. This could have brought small amounts of high-pressure polymorphs, like stishovite and rhyodite, to the Muongnong tektites. Clay pool sediments in the Muongnong area were preheated by radiation from the fireball. The fireball created a several hundred-kilometer radius viewshed. The area was later cloaked by a thick hot blanket of ejecta, containing the comminuted silt quartz grains, enabling even large Muongnong tektites to melt by conduction, over short time, without a temperature gradient. This ejecta layer buried tree trunks in the area, carbonizing them, explaining their attached layers of silt quartz grains. Splash-form tektites acquired their comminuted quartz cover upon landing. Later, evaporated groundwater, and water contained in the comet, created a tremendous downpour, making huge debris flow from the mountains encircling the Korat Plateau. In front, this created the low, terrace gravel pits, like Ban the Chang. When the low terrace flow in front stopped by desaturation, the gravel piled up behind, on the mountain side of the Mun and Chi rivers, creating the high terraces. The dust from the cloud continually falling on a now water-filled Korat Plateau, created the Yasathon soil, up to 3 meters thick, without graded bedding. The elevation map shows the landscape after flash flooding, behind and over the Nakhon Ratchasima basalt, leaving sharp eroded edges between the basalt domes. The last footprint was a gravity anomaly around the Nakhon Ratchasima basalt, the probable impact site. Read more in the summary chapter.